Now, suppose we have a linear map ahead from a vector space to another vector space, linear map of finite dimensional. Vector spaces. So let's data V1 up to Vn and when the prime S1 up to Fm is basic for V and W respectively. Okay. Then how do we form the matrix representation of this linear map? We write any basis element like this. Okay, here I write Fj, and then I write again Ji, and here from 1 to n, right? So this this becomes the jth column, ith column of the matrix representation. So the matrix representation of this linear map from beta to beta prime is the matrix Arj. Okay, Arj. So then, you know, the coefficients here from the gate, ith column, right? Yani linear görüntüsünü diğer bazda yazdığında elde ettiğim sayıları matrisi benim bu matrisin i'inci kalıbı olarak görüyorum. Ith column, so J1, J2, no. A1 I, A2 I, M I. Here J from 1 to M, right? Because I have M in vectors here, and this is an M by M matrix. Okay. Now, how would you write this using Tensor notation? Well, let's take a start. So we want start, we end start, and data prime start, which is F1 start, F start. The new basis is for V star and W star respectively. Then we can write the linear map as follows. Is the following gadget. How you see When this guy eats the vector EI, it gives us this expression, right? When AH eats this vector, it gives you this expression. So, when EI, so when, okay, so, this will eat EI and it will give us what? It will give us AJI FJ. So I should write FJ answer EI star. Unit 1 up to and. So just looking at this, I can write this. Let's check whether this is correct. So I need to check the following. When I feed this guy with EI, I should get that expression. Let's do this. So from 1 up to n, AJI, FJ, answer EI, start. I feed this guy with EI. If I do this, yeah, here, of course, we should take summation not only from 1 to n, but I'm sorry, except from 1 to. So we have to have double summation. 1 to n. Okay. So we have n times n terms. Okay. For each RG, I have 1 term. So we have this expression. What is the result of this? Well, summation from 1 to n, summation from 1 to n, AJI, and then FJ cancel EI star evaluated on this. But what is this gadget? Well, this is just right. This guy will be this one. Belki şeyde dikkatli olmak lazım. Şimdi buradaki bunu hep bu indeks hem şunu İK yapayım mı? Değil mi? Evet. Şimdi İK yapalım. Yani bu indeks İ değişiyor ama İK değişmiyor. So what is this? This is just EI star, it's EK, and then you just write this thing, this is a real number or element of our field, and we put this in front of this gadget. And what is this gadget? Well, it is 0 unless I equals k. Therefore, for each I, unless I equals k, this will be 0, and it will be 1 only if I equals k. So this is equal to the following. There is only one non-zero term, and this is for I equals k. So we have this summation just goes away. I have a, j, and then the only non-zero term will go with that I equals k, so I will write k here, and then I equals k, then of course, when I equals k, this will be just 1, so I will just get fj. But this is exactly right. If you compare with this, right? This is exactly just a head of EK, right? Right. Bu biraz garip olmuş. Değil mi? Burada J mantığı. Of course, instead of I can just write K. So, ahead of EK. Therefore, this is just ahead of EK. So, what we see is that, this gadget applied to this vector is the same as ahead applied to this vector. Right? This is a linear map. You apply it to the basic element EK, and what you get is just ahead applied to the same basic element. Therefore, this linear map and this linear map are the same. In other words, ahead is equal to this expression. Okay, so we check this. Tamam mı? Let's do one example. Sorusu olan var mı? Yani eğet buna eşit. Bu ifadeyi bir basis elemanında hesap ettim. Bunların eşit olması için for this two linear maps to be equal to each other, they should agree on every vector. But since they are linear, it is enough to check this on only basis elements, right? So I compute this one and this one on the same basis element in K for each K, and we see that this expression is just ahead of EK. Therefore, this linear map and this linear map are the same. That's it. All right, let's do one example. Now, suppose that ahead is the linear map from 2 by 1 vectors to 3 by 1 vectors, so that its matrix representation in the basis data, let's say I choose the basis for this, let's say this basis, and beta prime f1, let's say 1 0 0, f2 0 1 0, f3 is the sector 0 0 1. Is the matrix is this matrix. So A has beta prime kaça kaç olacak? Bu vektörleri diyecek, bunları verecek. Dolayısıyla şöyle bir şey olacak herhalde. Değil mi? Yani 3 çarpı 2. Here it is n by n matrix because it's from n dimension to n dimension, so it is n by n. Here it's from 2 dimension to 3 dimension, so it is given like this. Of course, since these are just standard basic elements, how this is given. So if I choose x, y to be just, well, this is just x times 1, 0, and 0, 1, and thus ahead of xy is what? It is just x times ahead of this gadget 1 0 plus şuna şey diyeyim, buna A matrisi diyelim. A matrisinin buradaki görüntüsü çarpı Y çarpı A matrisinin buradaki görüntüsü. So this is just x times what? 1 0'nun görüntüsü nedir? 2 0 4 değil mi? 2 0 4 artı Y çarpı eksi 1 3 5. Ya da bu tabii ki this is nothing but actually this gadget. So 2 0 4 minus 1 2 5 times x 1. Right? Değil mi? Şuna bakarsanız 2x eksi y 2x eksi y 0x artı 3y 0x artı 3y 4x artı 5y 4x artı 5y. So they are the same gadget. I can write any way I want. So what would be the tensor representation of this linear map? Well, I need to write down basis for the dual spaces. So suppose this is just E1 star, E2 star, and with the prime star, we just F1 star, F2 star, F3 star. So a head can be written as what? Can be written as just yani okay. A head EI pardon. Şuradan direkt yazabilirim. A head olacak. A head is just summation from I from 1 to 2, summation from J from 1 to 3, AJ I, FJ, Tensor, UI. So a head is just this gadget. Hesap yapalım bir tane. Mesela EHT bir hesaplayalım. Okay. So this is just A I from 1 to 2, J from 1 to 3, I, FJ, Tensor, EI, star. Okay, 1 1. Well, this is just a I. So this will be just, this thing will be just EI star evaluated on 1 1 and then FJ, right? So okay. Yes, EI star 1 1, it will be this one, and then I will have FJ here. Then I equals 1, so yeah, şöyle yazayım. J from 1 to 3, A, J, 1, E1 star 1 1, FJ, plus 1 to 3, A, J, 2, E2 star 1 1, Fj. What is E1 star on this element? Okay, now E1 star on E1 is 1, E1 star on E2 is 0, right? So 1, 1 is just E1 plus E2. So E1 star of 1, 1 is just E1 star of E1 plus E2. So this is just 1 plus 0, it is 1. Yes, so this thing is just 1. What about E2 star? E2 star 1, 1 is also E2 star. This is E1 plus E2. So E2 star at E1 is 0, E2 star at E2 is just 1. So this is also 1. So both of them are 1s. So this is 1 and this is 1. So what we see is that J from 1 to 3, AJ1, FJ plus AJ2, FJ. Okay, so let's see what they are. So AH11 is just J1'den 3'e kadar şey olacak değil mi? Yani A1 yok şurada 1 1 F1 2 1 2 right and 3 1 no A3 1 F3 right J from 1 up to 3 and then plus the same thing A1 to F1 F2 to F2 plus F no F 2 3 to F3. Bunların da değerleri nedir? A1 neydi? So this is the matrix. So A11 is just 2 F1 2 1 0 3 1 4 and then 1 2 minus 1 2 2 3 and then 5. So it is just F1 minus no plus 3F2 plus 9F3. So it is just 1, 3, and 9, right? Of course, this is the same thing as what? 8 times 1, 1. So look at this matrix. A was 2, 1, 0, 3, and 4, 5, 1, 1. So 3. Hangisi eksik? Şurası eksik. Şurası 1 oldu. 3, 9. Okay. Tamam mı? Hı. Şu mu? Bunlar şu toplamları yazdım. C eşittir 1, C eşittir 2, C eşittir 3. Burası hep 1. 1 koyduğumda A1 1 F1, A2 1 F2, A3 1 F3. Ama aynı değil mi? Yani E1. Evet. Burası aynı. Burası 1. Bu da 1 çıktı. Tamam mı? Yani karmaşık görünüyor ama aslında aynı şeyi farklı şekilde yazıyoruz. Hani şeyli tarafı yok. Hani gece 3'te birisi sizi uyandırıp şunu tensör gösterimini yazın dese yazamayabilirsiniz ama nasıl yapıldığı belli. Hani oturup sakince yazarsanız çıkacak bir şey, nasıl diyeyim, bir hani muhteşem bir fikir falan gerekmiyor. Yani. Sadece reçeteyi uyguluyorsunuz. Okay. Well, this association, so this associates a tensor representation in nerede bir tensor? Bu W'nun içinde, bu neyin içinde? V star'ın içinde, değil mi? So in W tensor V star to any linear map a hash from V to W. Okay? So whenever you give me a linear map from V to W, I associate a tensor in this vector space. Theorem is the following. This the above association is a canonical isomorphism from homomorphisms from the vector space form U to W. So to any homomorphism from U to W to write tensors to the vector space W tensor is I gave you how you obtain this tensor from the linear map, right? When you give me a linear map, I associate a tensor. You may object to the following. Here I said a canonical isomorphism, but then I did everything assuming I have some basis, right? I chose a basis for V and then a basis for W. Therefore, my map from this to this actually uses basis. Like, yani canonical deyince ne demiştik? Yani bir uzaydan diğerine giderken basis kullanmadan gideceksiniz. Mesela B'den B'ye identity. B'yi alıyorsunuz, B'ye götürüyorsunuz. Canonical mı? Ya da B'yi alıyorsunuz, sıfıra götürüyorsunuz. Bu da canonical. Başka da yok. Ama burada ben bir homomorfizmaya bir tensör karşılık verirken bazıları kullandım. Dolayısıyla da bu canonical lafı biraz şey duruyor, hani yanlış duruyor ama değil aslında. Şu yüzden this can be done without use of basis as follows. Ben öyle yaptım ama öyle yapmak zorunda değilsiniz. Şöyle yapabilirsiniz. Evet. Beta star'ı kullandık. Yani ama hani sonuçta beta prime star dediği şey beta prime'dan geliyor. Dolayısıyla hani bir basis seçti. Değil mi? Ama dediğim gibi aslında hiç basis seçmeden yapılabilir. Nasıl? Şöyle. Actually, I'll get a map from a canonical map from W tensor E star to form. Map issue. You give me this digit. So let's say I take one element here. What is this? These are elements of this star, WK, and then some dual element. And this is the finite sum over some index. Yani mesela burada here, this is the finite sum. It has 6 terms, right? So this is just a finite sum. I don't care how many elements are here. And this doesn't have to be basic elements only, just some elements. Okay? Where WKs are from W and FK start from V star. Tersten gideceğim. Yani buradan bir elemanı size buradan bir nesne vereceğim. Bu onu yapıyor zaten, değil mi? So this is an element here. It's a tensor, but I claim that actually this is an element here. Why? Because you see, whenever I have a vector in V, what is the value of this? Well, it is the following: summation over K. So VK tensor FK star evaluated at V. What is this? Well, this is the following. I just this is a dual element in V. So it eats vectors in V, and it's a vector in V. So we feed this guy with this vector. It gives us a scalar, and then I just put that scalar in front of this vector. Now this is a vector in where? In W, because these are elements in W. And you see, this way I didn't use any basis, right? Therefore, these two gadgets are canonically isomorphic. You don't need a basis. if you have a basis, then you can represent things in a form which are more useful, but actually you don't need. Okay, so this is a canonical map from this tensor product to this. Tamam mı? Neyle ilgili ona bakacağız. Yani bu nesne nedir? Bu W'da vektör, bu V'de kovektör. Dolayısıyla vektörleri ilgili, V'deki vektörleri ilgili. V'deki vektör verdiğimizde bunu biz nasıl tarif ettik? Dedik ki bu kovektör bunu yiyecek. Elde ettiğimiz sayıyı da bu vektörün önüne yazıyor. Sonra da toplayacağız. Bu lineer bir map. One must take. And this association is a canonical isomorphism.
Şimdi ne olduğunu kaplamak az çok biliyoruz artık da. İzomorfizm olduğunu nasıl?
İzomorfizm olduğunu açıklarız. İyi soru. Okay. Yani ben şunu yapıyorum. Teorem şu. Şuna isterseniz bu nedir? W tensor inside from V diyor. Değil mi? Nasıl değil mi? Bana bu nesne verildiğinde bunu elit görüyorum. Bunu nereye gönderiyorum? Gene ehliyete gönderiyorum. Yani gene ehliyet diyorum ama bu sefer ehliyeti V'den W'ya bir lineer map olarak düşünüyorum. Burada here of course cancel product FK star. Here I write a head as this gadget. Maybe I should write, you know, I mean, this is just 5 refrain. It's a linear map from V to W, and it takes a vector and sends it to this gadget. So this is a canonical isomorphism. Isomorphism of vector spaces. Which vector spaces? This vector space and this vector space. I need to prove that this map is linear. And it is also an isomorphism. In other words, it is an inverse, or it is one-to-one and onto, right? So one must prove that is linear. Second is one-to-one and onto. One-to-one ve onto'ysa o zaman tersi var ve tersi de lineer. Onu göstermiştik sanırım. Well, how can you show that it is linear? It is linear. Suppose I have two such expressions, A hat and B hat, what will be the resulting gadget? So this gadget at any vector, suppose A hat is this, and B hat is this. Atıyorum. Hani şunlara bir L okay. Bu ikisinin toplamına B'yi yedirmek ne demek? Boşlu olacak. So this is just this summation. Applies to B and no. Yeah, this plus this digit, right? Applies to B. But you see, these are two summations, and I can just combine them as a single summation. This is just actually a single summation, right? And then how this summation will eat this vector? Well, covectors will eat that. So this covector will eat that guy, and then obtain this, and then this covector will eat this guy, and you will get this vector. But you see, this is just the A hat of V, and this is just okay. And then also you need to observe that this is just lambda times this gadget, but again, it is something very simple because if you have lambda here, then you will have lambda here. And you will have that number here, so you can just take it out. You know, nothing will be difficult. Yine tahtayı değiştirmişim. So here, we should make it this linear. Okay. Şeye gelince, 1-to-1 and on-to. Okay. Well, first let's show that it is on-to. On-to. Why is that? Well, any linear map can be expressed like this. I did this in the first hour, right? Not first hour. I did this at the beginning of the class. We have seen that any linear map a hat, right, can be represented by a tensor, right? How I did this, I chose the basis for this, chose the basis for this. I wrote the matrix representation, and then using that matrix representation, I found a tensor, and that tensor just corresponds to this gadget. Therefore, we already shown that this map is onto. In other words, every homomorphism can be represented as a matrix. We have seen that. So we have seen that this is all. For one-to-oneness, I'll do this following. Okay. So here, to show that this method one-to-one, we use a general fact. Şunu göstereceğiz. Okay. Şöyle yazayım, lemma. If bu diyelim ki bir vektör üzerinden bir başka vektör üzerine yani B to W. This B and W doesn't have to be this, okay? Any vector space is a linear map. Linear map of vector spaces. So that this is onto and dimension B equal dimension W, and they are both finite. So if these are finite dimensional vector spaces with the same dimension, and if this map is onto, then this is one-to-one, and thus it's an isomorphism. Now let's see why this is true. Then I will write a more general fact, but first let's prove this kind of easy version. Yani iki vektör uzay arasında bir lineer map varsa ve bu vektör uzaylarının boyutu aynıysa, ikisi de 5 boyutluysa, aralarındaki map örtense izomorfizm olmak zorunda. Neden? Okay, proof of the lemma. Nasıl yaparız bunu? Zamanı var mı? Zamanı kalmamış. İyi, tamam. Teröriste düştün. Okay. Less than infinite.